All right, welcome back. Let us wrap up this first week of lectures. So we're going to continue more with talking about one-dimensional kinematics. We just introduced the idea of average velocity last time. We're going to build more upon that today. So last time, I believe we left off with a plot that looked like this. I think I said that this, if we pretended that I went jogging, I placed my origin at St. Mary's campus, and I made the positive direction my coordinate system as, say, down the road. I might have run, some distance away from St. Mary's campus, at which point then I turned around and returned to campus over the overall time of 46 minutes. And we asked ourselves, what about this can we learn, or what from this plot can we learn about my velocity, or the rate at which my position is changing? So I think we did this last time, but the questions were, when am I running or moving? And the fact that my displacement is always non-zero. From each of the data points to the next data point, the data points are changing location on the vertical axis. I started at the origin, then after 14 minutes I was 2 miles out, then after 28 minutes I was 2.5 miles out, then from 2.5 miles at 28 minutes I then went back to half a mile out at 32, and then back to the origin or St. Mary's at 46. So between each of those points, if I were to calculate a displacement, final position minus initial position, they would all be non-zero. Sometimes they'd be positive, sometimes they'd be negative. And then we talked about how the average velocity during those times is then my displacement between two data points divided by the time that has elapsed during those two data points. So for example, between the first two data points, I start at the origin, I end at 2 miles. That's a displacement of positive 2 miles. I divide by 14 minutes. That gives me an answer of 1/7 numerically. Then what are the units? The numerator is displacement, so it has units of miles in this case. The denominator is time, it has units of minutes. So then the answer, 2 divided by 14 is 1/7. So the answer is 1/7 miles per minute, or a 7-minute mile. And then you can calculate different average velocities for the different legs of my journey. The first two are positive because I'm always moving away from campus, away from the origin in the positive direction. And then the second two legs of the journey are negative. My average velocity is negative because my displacement is negative. I'm moving closer, I'm moving towards the origin in this case, or I'm moving toward in the opposite direction as the positive direction on my axis. And you can imagine if I kept going after 46 minutes, my displacement might start to go into negative numbers. And again, that just means I've passed the origin and I'm now moving on the other side. So perhaps I'm running down the other side of the road, away from campus, for example. All right, so let us, again, just to remind ourselves of kind of what that looked like. Let me just write that down. Remember that we had displacement, which was final position minus initial position. So displacement, where we called this a vector quantity because it requires you to have some sort of coordinate system laid down, because whether or not delta x, in this case is positive or negative, means something. It means in what direction the displacement occurred. Then we defined the average velocity last time as just the displacement divided by the amount of time elapsed. Average velocity. And I think that's where we left it. Units. Of course, going back to rule 2, the algebra of units follows the algebra of the numbers, or we can say that the units follow the symbols they're attached with. So the unit of velocity or average velocity must be the unit of whatever in the numerator divided by the unit of whatever is in the denominator. So that would be something like length per time, e.g. meters per second, miles per hour, kilometers per hour, would all be examples of average velocity units, or velocity units in general. Now, if I were asked the question of when in this plot does it appear like I'm moving the fastest, One way to do it is, of course, you could calculate the average velocity along all the legs of the journey and see which numbers are the largest. Remembering that even very big negative numbers could mean largest in this case. A large negative velocity just means I'm moving really fast, but in the opposite direction, away from whatever the positive direction is. We could also, interpret this equation and see how it connects to the graphical representation of position as a function of time. So again, if I just recopy it down here, average velocity is delta x over delta t. Where on this graph, graphically, is the delta x and where is the delta t? Let me actually zoom in here so we can see it a little easier. Let's look at this data point and this data point. I wanted to calculate the average velocity, delta x over delta t. How is that being represented graphically? Delta t, of course, is the time that's elapsed. So in that case, delta t is the amount of time that is elapsed. So this right here corresponds to delta t, for example, because that is the same as the length of the base of the triangle or the rectangle or the height of the triangle. So this length here corresponds to delta t. Delta x in this case corresponds to the displacement, or how, in this case, the value on the vertical axis has changed. So the the position started here and it ended here. So this corresponds to the displacement. Or I could say that this part right here corresponds to the displacement, the change in the vertical axis in that case. So you might see something here. You have this corresponded to delta t, this corresponded to delta x. So delta x in this case was the change in the vertical axis divided by delta t, which is the change in the horizontal axis. That may sound familiar because that is nothing more than, in terms of this graph, rise over run, or other words, the slope of the curve between those 2 points. The average velocity, if I pick 2 points as a start and end point and I draw a line between them, the slope of that line is delta x over delta y, or over delta t, rise over run. That slope is indeed just the average velocity. So when I look at this plot, let me just get another copy of it. When I look at this plot, for example, between data points 2 and 3, if I connect them by a straight line, that straight line has some slope. The slope of that line is equal to the average velocity between those 2 points. Similarly, if I look at the second and the third point, there's some change in displacement, and there's some change in time. If I connect those dots by a straight line, the average velocity is the slope of that straight line. In that case, it makes sense that the average velocity is negative in that case. It has a negative slope. You're moving back towards the origin from the positive side. And the only thing I'll say is, notice how here we have to be a little bit careful about names. And I think I even slipped up a little bit earlier when I almost said delta y over delta x, or rise over run, or y over x, or something like that. Because I think we're used to, in a mathematical class or a mathematics class, the horizontal axis is always x and the vertical axis is always y for whatever reason. But notice in this case it's a little bit switched around because now the axes have physical meaning. The horizontal axis in this case corresponds to time. where the vertical axis corresponds to position, which we're using the symbol x in this case. So in this case, rise over run is something more like delta x over delta t. In general, it's just delta, whatever the y-axis is, divided by delta, whatever the x-axis is. So something to be careful of. Don't just immediately think, oh yeah, slope is delta y over delta x. Because in a math class, those symbols might have different meanings than the way I'm using them, for example. All right. Right, if we were to take this a step further, I could ask, okay, if I were to plot then as a function of t, what then is the average velocity between 0, 14, 28, 32, 46 minutes. And this would be something like miles per minute or something like that. And this is in minutes. I don't care so much about getting this exactly right, but we can kind of eyeball it and just, if you just want to look at how the average velocity compares, we can just look at the slopes. So it looks like the slope is pretty steep at the beginning. So I might say that the average velocity is something like this. Then from 14 to 28, the slope is still positive. It's still pointing upwards, but it's not nearly as steep. So it might drop down to something like this. Then the slope becomes negative, and I actually know that it's the same value, but now just negative as what it was originally. So it might drop down to something like this and go on to t equals 32. And then it looks like going from 32 to 46, the slope is still negative, but not quite as steep. So I think it actually goes, it's just a mirror image. So I think actually it's just this in this particular case. So this might be how, by looking at a plot of position versus time, we can actually turn it into a plot of velocity, or in this case, average velocity versus time. Okay, so the takeaway here is that average velocity is the slope of the line connecting 2 points on a position versus time curve. How the position is changing as a function of time is the slope of the curve, that is the average velocity. So here's a problem to think about. No, because I haven't shown it yet. Here's a problem to think about. There are two plots, and I'll tell you only that one of them is the position as a function of time, and one is the velocity as a function of time. My question to you is, which is which? So here, I would say that the top plot, do I have copies of this? Oh, I do. Let me actually throw it on my iPad. Switch over to this. So if I were to look at these, again, if I think of velocity being the slope of position, or the average velocity being the slope of the position between 2 points, I could just try to look by eye and see if I could argue out one over the other. If I look at the top plot, it seems that in this middle region, I'm essentially starting at some point and I'm going out, and I'm not changing in the vertical direction. The slope of that curve is very, very close to 0, if not exactly 0, which happens to correspond to the value of this plot down below. It has a value equal to 0. So if the average velocity is the slope of position, the value of this appears to be matching the slope of this. And if we look at the other parts of the curve, you can convince yourself that that is indeed true. If I look at, say, the third leg of this curve, it seems to be going down towards the origin, and it seems to be a decently straight line, which has a fairly constant slope. And then if I look at the bottom curve, I notice that it has a value that is fairly constant. Its value on the y-axis is not considerably changing. So it has a value that seems to correspond to some sort of constant. So again, that jives with the idea that this is position and this is velocity. Maybe just average velocity. And then we can just to make sure we're completely clear on this, if I look back at the top curve, now thinking, let's reason it out and think, okay, if this is indeed the position, that means that the position looks like it's starting at the origin, it's increasing, and then kind of gets to some positive value. But it does so in a way where it seems to be going up at a constant rate and then kind of levels off. So it looks like the slope is kind of positive, it's curving upwards, and then it flattens out and becomes horizontal. So if I had to think of what would be the value of the slope in those regimes, I would think that the slope is some positive non-zero value, and then it becomes zero because it flattens out, and a straight horizontal line has a slope equal to zero. There's no rise, even though there's a run. And that seems to be what's going on here. It seems to be a constant positive value, and then kind of near the end, it kind of drops down to zero. So again, emphasizing the idea that the slopes of position is the values of your average velocity between 2 points. Now, all this really is saying, again, the idea here, it's not just graphs, but we're trying to connect the ideas between position and velocity. So we can think of, if we go to the board, record please. Suppose that we have, Einstein the observer, and he has laid down a coordinate system. So he has placed himself here at the origin. He's defined the positive direction to be going over to the right, and therefore the negative direction is over to the left. He has some tick marks laid down. And suppose he observes me just walking. And he wants to ask, if I want to calculate Dr. Lee's average velocity, say, over the span of 1 second, how might I go about doing that? And he can use his coordinate system to do that. So if I start at 2 meters, and over the course of 1 second end up at -8, so 1 Mississippi. All right. So I started at 2, I ended up at -8. If I wanted to calculate my average velocity during that time, I would say that, it's delta x over delta t, delta x final minus initial, -8 meters, minus positive 2 meters, final minus initial, divided by the amount of time that elapsed, which in this case was just 1 second. -8 minus 2, in this case, is then just -10 meters divided by 1 second. -10 divided by 1 is just -10. Then units follow the algebra of the numbers. 10 divided by 1 is 10, or -10 divided by 1 is -10. So therefore meters divided by seconds. Meters divided by seconds. So I would say then my average velocity in that case was -10 meters per second. And if I wanted to think of, thinking ahead when we talk about vectors, if I wanted to have this little arrow represent my velocity, I might have it then pointing to the negative direction. Again, remembering that this number is telling me 10 meters per second, that's how fast I'm moving. But if I ask myself, what direction am I moving? The negative number, all that means is that I'm moving in the direction towards the negative numbers. This was the positive direction. This was the negative direction. A velocity of -10 meters per second means that my arrow points to the left. Now you can imagine if we did this in the opposite order. Suppose I started at -8. Over the course of 1 second, I end up at -2, or sorry, +2. Then what changes here? In this case, it's not -8 minus 2, but I started at -8, I ended at +2. Final is 2 meters minus -8 is my initial position. That then becomes 2 minus -8, so that's +10. At the end of the day, then my average velocity is just 10 meters per second. So again, I might put the arrow like that. Again, the magnitude, it's 10 meters per second. In what direction am I moving? Since this is positive, I'm moving in the positive direction, in this case, for this coordinate axis. As is determined by my initial position being at -8, and my final position being at +2. Let's not bother with the calculations. You could imagine if I were to do the same thing, but maybe I do it in half a second. So instead of me walking over 1 second, maybe I do it in half a second. Obviously, I'm moving faster when I do that. I'm still moving in the positive direction, but I might represent it as a larger arrow, for example, compared to this one. Because I'm moving towards the right, but now I would have a larger average velocity. In that case, if I did this in half a second, then this would just be 0.5. This actually would just change to 20 meters per second. So velocities, I think, the direction of the arrow, I think, is a little bit easier to grasp compared to what we're going to be doing next. Because the velocity arrow is just, whether it's negative or positive, is just telling you what direction I'm moving in. If I'm moving in the negative direction, then my velocity is negative and my arrow points this way. If I'm moving towards the positive direction, then my velocity is positive, and that's just saying I'm moving in the positive direction. If I were to plot this on a graph, all that would represent is that the slopes would either be positive or negative, depending on whether I'm moving in the positive direction or the negative direction. But actually not done. When is the average velocity actually giving us a decently accurate answer? It's not always actually giving us a super accurate answer. Because again, remember, the average velocity is defined as whatever is going on at the endpoint minus wherever you started, and how long it took you to get from the starting point to the end point. So again, if I'm doing this in 1 second and I'm moving at a constant rate, that is actually pretty accurate. My average velocity is my actual, that is a completely accurate way to describe my velocity. A way to think about this is, suppose you're in your car, you have cruise control on, you're coasting at 60 miles per hour. Your average velocity is then 60 miles per hour. You're always moving at 60 miles per hour. Every time you look at your speedometer, it would show 60 miles per hour. But what about if I am doing stuff in between my starting point and my end point? Like perhaps I'm walking in one direction, and then I speed up for a little bit, then maybe I stop for a little, and then I keep going. All that information is lost if I just use the endpoint and the starting point to calculate my average velocity. It would just be saying, over the course of however long all of that took, you covered that much distance, and so on average your velocity was some value. Even though while I was going from my start point to my end point, maybe I'm doing other things as I go around. Maybe I could even turn around at some point. So you can see that if the average velocity, if you're using a delta t, if you're using something that's a little bit too big, you're losing information in between those two start and end points. And I think I ended the last lecture saying that you might think about this. For this position, plot here for me jogging, this is me recording data every 14 minutes. But what if instead I had my Apple Watch or Fitbit recording data every second? It might look something like this. It would still agree with the answers I got every 14 minutes, which is the black dots there, but the curve might have some more interesting features along the way as I go between the data points. And so you might ask that, what about that information can we learn about if we wanted to know something about the velocity over a more refined period, rather than knowing about my jogging speed every 14 minutes or in increments of 14 minutes? Can I say something a little bit more refined, like what is my average velocity over every minute, for example? I could calculate an average velocity every minute. And that would give me a little bit more information, so as I sped up and slowed down, like you can kind of see that here. It looks like I jog really fast at the beginning. My displacement is large. I'm getting far away from the origin very quickly. But then I am out of breath and I start to slow down a little bit. I'm not covering quite as much distance in the same amount of time, over this period of time compared to what I did the first 10 minutes or so. So this is the idea that we could just take the average velocity and we could calculate it over a more and more refined period. And the hope is that at some point the average velocity that we're calculating actually becomes incredibly accurate and actually does perfectly represent the velocity of our motion during that interval. So here's the idea. Where is this? Okay. Suppose this is my position versus time graph. And I want to know something about suppose it's me running. And I want to know something about what I'm doing around t equals 1. Let's say these are minutes. So t equals 1 minute, for example. One way I could do this is I could use my start and end points as t equals 0 way over here and t equals 2 way out here, and calculate an average velocity from that. And you might get something that looks like this. If I were to connect those two endpoints by a straight line, that straight line is an approximation to how my position is changing over the course of those 2 minutes, while the blue curve is what actually happened over the course of those 2 minutes. So you can see that the two curves do not look very similar to each other at all. The approximation by using those two very farly spaced apart endpoints does a pretty terrible job at capturing what is going on from t equals 0 to t equals 2. And so I would particularly in this case not necessarily know if I should trust anything it says about what I'm doing around, say, t equals 1 minute. But the idea here is that instead of using a big delta t, we could use a somewhat smaller delta t. So let's essentially zoom in. So now I'm zooming in between 0.8 minutes and 1.2 minutes. So I've zoomed in a little bit. So now I'm not going from 0 to 2, now I'm going from 0.8 to 1.2. And now I have a new start and end point. So the time elapsed is now shrunk. I'm now focusing in on a smaller interval of time. So my delta t is shrunk. And my displacement has also shrunk because I'm covering, now I'm looking at a smaller piece of time. Originally, from 0 to 2, my position changed from something like 0 to 16. Now, if I just focus in on what's going on between 0.8 and 1.2, my position is changing from something that seems like, 0.5 up to 2 or something like that. And notice that the two curves got a little closer to one another. The approximation I'm making by just drawing a straight line is getting a little bit more accurate compared to what is actually happening, which is the blue curve. So why stop there? Zoom in even more. So now I'm going from 0.9 to 1.1. I've zoomed in a little bit more. And notice that, again, the curves are starting to get closer and closer to one another. The average change that I'm measuring by the solid orange curve, which is an approximation, is starting to actually become a little bit more accurate with what is actually going on in now the smaller little interval of time. Let's keep going. Zoom in even more. Now it looks like I'm going from 0.98 to 1.02 minutes. So over the course of now 0.4 minutes. So I'm really zoomed in now compared to what I was originally. And then the gold line, again, I'm just taking the endpoints and drawing a straight line between them. And then the blue curve, which is now becoming hard to see, is actually starting to essentially overlap the gold curve almost perfectly. It's not quite perfect. I can kind of see the blue curve a little bit. So it's not quite accurate, but any information I wanted to calculate from using that much simpler orange curve, I would actually start to trust in this case. I would say that that orange curve accurately is representing what's going on in this smaller interval of time. So if, for example, I used the average velocity that I would calculate, or the slope of that orange curve, that seems actually fairly representative about how fast I'm actually moving around t equals 1. And of course, why is that as small as we can go? Suppose I had a really, really precise watch that now I'm measuring from 0.999 minutes to 1.001 minutes. And now you've noticed, now I've shrunk delta t so much that essentially what I'm seeing, if I just connect the endpoints by a straight line, I'm seeing that that approximation actually is following the true curve almost exactly. There is a blue curve here, but it's beneath the gold curve in this case. So if I wanted to, say, calculate my average velocity, which I could use my displacement, which looks like it's something like 1.004 minus 0.996 maybe, or somewhere close to that. So that would mean my delta x. And then my delta t in this case now is something like 0.0001 or something like that. So I've shrunken my delta t. As a result, I've kind of zoomed in on the plot around a particular point, and notice that as we zoomed in, we eventually reached a point, or reached a regime, where the approximation that we were making, the gold curve, was perfectly representing what my actual motion was doing. Do I go more? Oh, I don't go more. Now, in this case, I went from 0.999 to 1.001. You could ask, why do you even need to even stop there? Could you even keep going more and more? And of course, if I had, an incredibly accurate, cesium atom watch or something like that, I could refine, and why have my delta t just be 0.001 minutes? I could go down to, a microsecond, a nanosecond, a picosecond, and refine more and more as my delta t shrinks more and more and more. And then it would come to a point where I'm essentially defining what my velocity is, calculating my average velocity over that incredibly small interval. That average velocity would essentially be telling me the velocity that I'm moving, at some given instantaneous point. And that is the idea here. So let us define the instantaneous velocity, which is just going to be defined as just v, with no subscripts. As the velocity at a given point in time by the following. Now, those of you who have taken calculus know what I'm about to do. Those of you who have not taken calculus, don't worry, I'm going to explain all these symbols. So I'm going to define the instantaneous velocity as the limit as delta t goes to 0 of delta x over, oops, actually I'm going to write this a different way, as v average, which is the same thing as the limit as delta t goes to 0 of delta x over delta t. That's just the definition of the average velocity. So what this is, this limit thing, which the Calc 1 folk will see probably next week, is what I'm doing is I'm doing exactly what I just kind of walked us through with the plots before, where I'm focusing in on smaller and smaller little time intervals and looking at the displacement over those smaller and smaller time intervals. And I'm calculating what the average velocity is over those smaller and smaller time intervals. So since the average velocity, remember, is just the slope of the position as a function of time curve, I'm asking what is the slope over a very more and more refined region of time up until the point where I'm essentially just saying what is the velocity at a given point. That is the instantaneous velocity. The velocity of essentially at any given point in time. Or you could think of it as the average velocity over an incredibly tiny little time interval. In a way, we will rewrite this in calculus. Rather than using capital delta, capital Greek letter delta, we call this dx over dt. So this is what is called the derivative of x as a function of t. In this case, the derivative of position as a function of time. Derivative is just a fancy word for slope. In this class, you can essentially just think of derivatives as slopes. So v or dx dt equals the slope of x as a function of t at a point. And this relates to what the Calc 1 folk will learn soon. This relates to something that's called the tangent line. So let me just kind of draw that out and sketch an example of this. So again, you in a calc class, you will go through the nitty-gritty kind of gross proof detail on kind of how to define a derivative. For this, you can think of a derivative as we started with some big delta x over some big delta t. We kept zooming in and in and in to some smaller delta x over delta t. We zoomed in even more to some smaller delta x over delta t. We zoomed in even more to some smaller x. And that eventually becomes what we call the derivative of x as a function of t. So we're just looking at the displacement as a over some time interval over smaller and smaller time intervals. So suppose I have some plot here that is my position as a function of time. It's doing some crazy thing where it seems to be going out from the origin, it stops, comes back to the origin, goes past the origin, turns around, comes back, and kind of oscillates back and forth. We could ask ourselves about the velocity of this object at any given moment in time. Like, for example, what is going on, right here? If I wanted to say what my velocity is at that given moment, what I'm talking about is the instantaneous velocity. You could think of it as taking the average velocity over a very, very refined, small little period of time. So again, in calculus, you will learn that this is the same thing as a tangent line, which is essentially a line that just kisses the function. You can imagine it just, like we're a sled going down a hill. That sled is just perfectly kissing the side of the function or the hill as it goes down. Similarly, if I were looking at this point right here, the tangent line would just kind of kiss the function where it touches the function only at that one point and nowhere else. And these lines have some slope. There's some slope that this tangent line has, and that is the instantaneous velocity. There is some slope, some rise over run for this curve, and that slope is the instantaneous velocity at that point. that is the entire idea behind instantaneous velocities, is we're just doing it over a very, very refined period of time. Okay, so conceptually the takeaways is that velocity is the slope of position. Actually, I'm just going to, well, I already wrote that down here. Since I already wrote it down, I will just highlight it. Velocities are the slopes of positions. If you're plotting position as a function of time, the velocity is then the slopes of that curve. Because it is telling you how your position is changing, or how the position curve is changing over time. So I have a question for you to think about. If this is a position plot, sketch the velocity plot as a function of time. All right, you hopefully have paused it and thought about this a little bit. Now, let's actually go through the answer. So if this is position, where it looks like maybe the unit is meters, and then here the time axis has units of seconds. So then in this case, the unit would be meters per second for velocities, and then I'm doing it as a function of time, so it remains seconds. I could ask myself, what is the slope of these curves? And that corresponds to the velocity. So for this first section, it's pretty straightforward. It looks like it's essentially a straight line. So that it seems to have a rise of 1 meter. It has a run of 1 second. 1 meter divided by 1 second is 1 meter per second. So I might write this as, if this is 1, then maybe this is the velocity during that increment of time. Then if I go back up to the curve, I'll use a different color. Going from the next 2 points, those points look like the displacement does not change. I start at 1, I end at 1 over the course of 1 second. The rise is 0, even though the run is 1 second. So in that case, the slope is 0 in that case. Now it looks like the next increment, I'm starting at 1. I'm going all the way down to -1. So my displacement, final minus initial, that looks like it's -2 is my rise. My rise is -2, the numerator. The run looks like it's half a second. So -2 meters divided by half a second would be -4 meters per second. So in that case, let's see, if that was 1, I shouldn't have separated this so far, if we want to be accurate. So let's call this 1. So then, and then this is 2, 3, 4. So then this is -1, -2, -3, -4. So then it looks like it drops down to -4 at this point. And then last but not least, then the final leg of the journey, it looks like I start at -1, I remain at -1 over the course of 1 second. So again, rise is 0, run is 1 second. That slope is 0 in this case. So I would say that is my velocity as a function of time plot, doing it entirely based off looking at the slopes of my position as a function of time curve. Which mathematically I can think of, if I write this over to the side, I can think, given position, if I want velocity, the way I go from from position to velocity is by taking a derivative. So think of this just as going from position to velocity, you take the derivative. The derivative of position equals velocity. All right. Now we could ask, what about velocities? How can velocities change? You know, you can imagine if I'm speeding up or slowing down. I'm sometimes moving faster than I am at some other points. That means my velocity itself is changing. The good news is that we can define everything in exactly the same way as we did before. So define the average acceleration A average. And we're going to define that as where the average velocity was displacement over time elapsed. We're going to define this as delta V over delta T. Or if I want to write it out, the velocity at some final time minus the velocity at some initial time divided by the difference in time, so how much time has elapsed. And why stop there? We can define the instant we already did that. We can define the instantaneous acceleration. In this case, in the exact same way. The instantaneous velocity was a limit of the average velocity. So A, which is going to be the instantaneous acceleration, and maybe I'll just say that up here, A, we're going to define as the limit as delta t goes to 0 of the average velocity, which again is just the limit as delta t goes to 0 of delta v over delta t, which before we called that the derivative of, for velocity we called it the derivative of position, for acceleration we call it the derivative of velocity. As a function of time. How is the velocity changing with time? Are you speeding up? Are you slowing down? When we get into two-dimensional motion, we'll learn that this also means changing directions. If I turn left or right, that is an acceleration. And we can bring up through an analogy where x of t, remember we got that, we took the derivative and got velocity. And then now I'm saying we can take the derivative again and get acceleration. So similarly, where v, I can think of this as velocity, the arrow going the other way, velocity is the slope of position as a function of time. Again, similarly, A is the slope of velocity as a function of time. If I make a plot of velocity as a function of time, the slopes that I calculate are then the accelerations. Just how the slopes of position as a function of time were the velocities. Units of acceleration. Again, it follows the units that define them. So with some velocity over time, so I would say this is, the unit is the unit of velocity divided by the unit of time. So for example, velocity might have meters per second, time might be seconds. The first guy is a fraction, so I could always just say this is meters per second times seconds, or something like meters per second squared. So in this class, we will see meters per second squared a lot. It's a velocity divided by a time, which I kind of like. I like to think of it that way, just to remind myself kind of physically what's going on. When meter per second squared might feel and seem a little abstract, but really all it's saying is the part I just highlighted, where it's a velocity divided by a time. How is the velocity changing over time? Which, when you put all the units together, is then just meters per second squared or miles per hour squared or whatever weird unit you are. And again, luckily we can just draw from everything we've already done. I don't have to really teach anything new, because I can also say that A is a vector quantity. Again, meaning that the sign matters. A positive acceleration means the velocity is changing towards the positive direction. A negative acceleration means the velocity is changing towards the negative direction, which that is a little bit more abstract to envision. All right, so I'm going to take this off to erase this mess. And we're just going to try to reason out. Einstein has returned with his origin in his coordinate system. He's going to now measure me again with velocities, and we're going to also now think a little bit about what my accelerations look like as well. My cursor's in the way. So let's take the simplest example of I am moving to the left in the negative direction. And suppose I am moving at a constant velocity. So I'm just casually moving at a constant rate. We know that since I'm moving in the negative direction, I'm moving towards the negative numbers, my velocity, if I were to calculate a number, it would be negative. I might also represent it as arrows. But here I'll lay down two arrows to kind of represent what was my velocity kind of when I first started walking, and if my velocity changed, what is my velocity when I stopped walking? Let me hide these. So in the case where I'm moving at a constant rate towards the left, my velocity arrows really are not changing in length. So if I were to ask how is the length of these arrows changing, they're not. So I would say in that case, the acceleration is 0. The acceleration is how velocity is changing. Velocity is how position is changing. Velocity and position are a little bit easier to envision. I'm moving towards the left, my velocity points towards the left in that case. But with accelerations, what I'm saying is, since my velocity is not changing magnitude, I'm not speeding up or slowing down or changing directions, these arrows are remaining the same length. So as I walk towards the left, the rate at which I walk does not change. I have no acceleration. Now suppose instead I had this case. Suppose I start walking, but then I speed up as I walk towards the left. In that case, I might say that I start walking, at this rate, and as I walk, but as I speed up, I might end up walking at a much faster rate. So my velocity, since I'm still walking in the negative direction, still points in the negative direction. But now I'm doing so at a faster rate at the end compared to what I was doing at the beginning. So then if I wanted to think, how are my velocity arrows changing? Since this guy is smaller, the arrow is clearly getting bigger. So something has changed this velocity vector. Or rather, I've accelerated. And I've accelerated in that direction as well. I'm speeding up, in this case, towards the left. My velocity arrow is growing to become bigger to point towards the left as I speed up. Again, this is telling us how these guys are changing while these guys are saying how my positions are changing. Similarly, if I were to say start over here, and I start walking fairly slow, but then I speed up towards the end, I might say that since I'm moving towards the positive axis, my velocities are positive numbers and pointing towards the right. I again noticed that my my arrow started small and got bigger. It grew, so it changed. Over the course of time, it changed. Velocities can only change if there's an acceleration. And since it grew and got bigger while pointing towards the right, I would say my acceleration then is also positive. And we can kind of imagine this if we just think of simple numbers. You know, if in this case my velocity was, say, 10 meters per second, positive 10 meters per second, or over here it was only 5 meters per second, and this was over the course of, say, delta t equals 1 second, then I might estimate my acceleration, or in this case it would be more an average acceleration, as final minus initial, so 10 meters per second minus 5 meters per second, divided by the total amount of time that has passed, which is 1 second. 10 minus 5 is 5, divided by 1 is 5. I think I said that wrong. 10 minus 5 is 5, divided by 1 is 5, and then meters per second divided by second is meters per second squared, or positive 5 meters per second squared. My velocity has increased over time. And then you should try it on your own. Use the same numbers, but have both velocities be negative. You should find that the acceleration then is something like negative 5 meters per second squared, because the velocity vector is growing towards the left. Now here's the trickier one to kind of reason out. Suppose I start moving really fast towards the left, but then by the time I get to the other side, my velocity has decreased so that I'm not moving quite as fast as I am over here as how I started. What is my acceleration, or what if I were to put my acceleration down? Clearly my velocity has changed. These arrows are not the same length. My velocity has changed. So I need to put down this arrow in some way, but do I point it towards the left or do I point it towards the right? And then can I argue why? So again, we could use simple numbers. Maybe let's just use some simple numbers to estimate this. Again, suppose this is now negative 10 meters per second. Negative because it's pointing towards the left. And this is then negative 5 meters per second. So I'm still moving towards the left, but not as quickly. And again, suppose this happens over 1 second of time. I could then estimate my average velocity as final minus initial divided by the amount of time that passed. Final is negative 5 meters per second minus the initial, which is negative 10 meters per second, all divided by 1 second. Negative 5 minus negative 10, so this ultimately becomes 10 minus 5 divided by 1. This becomes plus 5 meters per second squared. So again, since it's a positive number, I would point this towards the positive direction. I would say that my acceleration vector points towards the right. And again, what this is saying is it's saying how the velocity vector is changing. It started really pointing towards the left, and now it's not quite pointing towards the left as much at the end. You can kind of think of this, so the acceleration is happening in the opposite direction. This would be an example of slowing down. So you can kind of think of the acceleration as pulling back on the velocity. I'm really trying to gung-ho it, but the acceleration is saying, hold on a second. Don't go so fast. Only go this fast. Brakes in your car is essentially this. The brakes in your car are trying to accelerate your car in the opposite direction and ultimately slow you down. So we'll do some more examples of that in future lectures. Oh, and I am perfectly on time. So that's where I'm leaving it. Great. We've completed 1 week. So next week, we're going to build up on this a little bit more to help build our intuition with this sort of stuff, and then work up to the kinematics equations, so put a little bit more math behind what we're talking about. But right now, it's very, very conceptual, and try to review and connect kind of conceptually how these three quantities, position, velocity, acceleration, relate. And then if you were to given plots of these things, how you can identify one from the other on various plots. And your book has a bunch of examples, so I would recommend looking at the book for some examples on that as well. All right, good. I will see you soon.